We will now look at the GCD test for nested loops and multidimensional arrays. And we will, as you have noticed, there are quite a number of slides in this lecture, and the reason is that we will look at different steps to create certain matrices, and they are most easily illustrated, this the algorithm to do this, using an example, or different examples for different things that we want to achieve. You do not have to be able to solve such problems at the oral exam, but in the questions.pdf I will write what is needed to be known. What you need to know. Okay, so let's look at this. First, we use something called a unimodular matrix. And a unimodular matrix, it's a matrix for which we can, it should be an integer square matrix, and we should be able to compute its inverse, which also should be integer. And that means that its determinant should be plus minus 1. Okay, so why do we want that? Well, say we have a loop nest, and there is a data dependence between iterations in the outermost loop. So we want to get rid of them. Then we will create a new loop nest, or at least try to. It's not always possible. We will create a new loop nest without data dependence in the outermost loop. Okay, so we use a transformation matrix that will reorder the iterations. And when we have found this transformation matrix, we can, the compiler will notice that certain loops can be run in parallel. But then it needs to create a new loop nest, obviously, that will perform this. And to compute the new loop bounds, to compute the loop bounds of this new loop nest, it needs the inverse of this transformation matrix. So that's the reason why the transformation matrix should be unimodular. Okay, and if we multiply two unimodular matrices, then the product is also unimodular. And what we will start with is a matrix with all the dependencies. One row for each. We will come to that later. But to solve the GCD test, we use something which is similar to a Gauss elimination in systems of linear equations. Okay, and then we create another matrix that is, which has basically zeros, numbers here and zeros there. Okay, and so that we can eliminate one at a time. Okay, and determine if, in this case, if there is a solution at all. And we start with this, and actually we start with I, and we have this, and we have this. Okay, so what we want to do is to find this U and S. So this one should be, it should be used to easily determine whether there is a solution and to find the solution as well. And we do that by creating a unimodular matrix. This is not the one for doing the parallelization. This U is for finding this so-called Echelon matrix. and we start with the unimodular matrix, the identity matrix, and manipulate. I mean, this we start with the same A that we had from the dependencies, and manipulate it until the right hand side becomes an echelon matrix, and we manipulate it using operations which are expressed as unimodular matrices, and that guarantees that this one is a unimodular matrix. Okay, so there are some elementary operations, and what we want to do is to multiply a row by -1 and interchange two rows and add an integer multiple of one row to another. Okay, so I will go through this quite quickly, and we simply pre-multiply the existing, some existing matrix with such an elementary matrix. Okay, and there are different operations that we can want to do. Okay, and well, I will we will soon come to what we will use this for. So the echelon matrices, it is what I mentioned before, that there are zeros in the lower left part. It's not exactly a LU decomposition, but it's similar. I mean, the idea is to be able to use the equivalent of Gauss elimination to find a solution to the Diophantine equation. Okay, and the definition is, well, it's written here, but it can also be seen here, namely that the number of rows with leading zeros is it increases or is the same. Okay, so this is the algorithm for producing these echelon matrices if we have the one A matrix that we had from the dependencies, and we set U to be the identity matrix and S to, a copy of A, and then we perform this. It's not very complicated, but we need to do that. This is typically a computer that should do it, such as compiler, and not by hand. But we can show it by hand anyway, and we can start. We can start with this, and we start with the identity matrix as the U. This is the same, and I will not explain what happens in each, but we will just see the progress. Okay, that's what we start, and we create these elementary matrices to manipulate. Basically, it's S that we want to create or manipulate, and U comes as a result of how we do that. Okay, so like this, and then we need to, at this point we had that, but we cannot have the zero row there. It must be interchanged, and now we have this. And then we can stop this, and now we can use the S to determine if there is an integer solution to this equation. And if there is, we are then interested in if this integer solution is within the loop bounds. Okay, so what we do is first we have the two references, and we had this like this: I j times I minus b, and like that. But we write it like this instead because it's more convenient. Okay, and we had a loop nest before. We said that there were m loops in this, but now we let m be twice the number of nested for loops. Okay, so we say that x is m vector. Okay, so how can we solve this? Well, we find u and s, and then we can solve it with, I mean, in this way instead. We solve t times s is equal to this c. And if there is a solution, then we can compute the solution to this one by multiplying t and u. Okay, so what we have found then is an integer solution to this equation. And what we need to do then is to take this integer solution and put it, I mean, to check if it is within the loop bounds. Okay, so an example. Say we have this from the beginning, and we can find this echelon matrix, and then we solve, we solve this. Okay, and we find this solution, and then we find the solution to this one, like this. So we take the solution to the previous equation and multiply it by u, and then this is the solution to this one. Okay, and that is what we will check if that solution is within the loop bounds.